a lot, but we might get to use it a couple times. I did hear a question. AJ, what's that? I have to give you this?
No, I.
Oh, can you believe it? Yeah. Okay. All right, cool kids. Section 5.3. Here's the dealio. I don't know if I introduced it with your class or period 5. Sometimes I get you guys confused as far as what I say when I say it. But section 5.1 and 5.2 were building skills of how to play with trig functions mathematically in a legal way. Common denominators and multiplying and factoring and simplifying and plugging in to change it up. Section 5.3 says let's give you like a place where you need to do that. Let's give you a practical application. It's going to be necessary to use those skills that you've been playing with. Doesn't mean that you had to have mastered them. Doesn't mean that you had to have perfected them. But I think almost all of you, to some extent, should have improved with at least being familiar with seeing trig and realizing that we can change up what it looks like. You should have improved at least somewhat in being able to play with those trig expressions. So, let's see if we can put that to good use today. But first, before we start playing with equations that are going to be tricky and need those substitutions, I can show you. I can give you a quick foreshadowing. Hold on. That one's a little too easy. How about this one? If you were to see an equation like this, and you were supposed to solve, first of all, it's not a t-proof. And we cannot make that match that. It's impossible. It's not a t-proof. Solve. How do we get x by itself?
Divide by cosine.
But we can't. Like, you're used to that, right? When there's something next to the x, just divide by it. We can divide by the 3, but that x is inside. Okay, so how do we undo trig? Well, we're going to need that back here in the workspace. How do we undo trig? How do we solve this? Divide by sin? No. Inverse. So first of all, we have to remember trig inverse. Trig inverse is how we undo trig. There's a sign. The x is stuck inside the sign. We have to undo the sign. Sign inverse. Okay, first of all, how do we undo trig? Inverse trig. And then coming back here, but what are we going to do to both sides? We could square root both sides, but do we do sine inverse or cosine inverse?
Cosine.
Neither yet. Change one, using your skills, change one, transform one to be in terms of the other so that we don't have to worry about having both. Can we make sine squared something with cosines? What does sine squared equal?
1 plus cosine. 1 minus.
1 minus, oh, we could change that one. I was thinking changing this one. So change sine squared to 1 minus cosine squared of x. Or you could change cosine squared to be 1 minus sine squared of x. We have to change one to be in terms of the other, then we can combine, and then we can solve. But it would be impossible to solve as is without changing it up, without transforming one side or the other. And we'll see other ones like that. But first of all, as you guys notice, we kind of got stuck even with the, hold on, how do we solve something like this? Basic. Sine of x equals 1/2. We had to review that first. We have to review that first. So, if you were in your calculator, when you were in your calculator, what's an example of an answer that you might have had when you were undoing the sign using inverse? Inverse sign. So you got x equals sine inverse of 1/2. What's something that you guys got? 30?
Yeah.
Good. What mode was Chris in if he got 30 degrees? Good. What could you guys have gotten if you were in the other mode? Okay, pi over 6 is a good answer. Technically, you would have gotten this nasty decimal that approximates pi over 6, right? Does anybody have that nasty decimal close by? 0.524?
Yeah.
Double check. That's the decimal.
Yeah.
Good. Okay, so those are two different answers. So first of all, we can have two different answers based on the modes. We already know that that's kind of a thing. But here's the point, guys. Each of these represent how many places in the unit circle? Even though there's two different answers, how many locations? Just one, right? Just 30 degrees. Just pi over 6. One location. So inverse sine is always going to give us just one location, just one angle, right there. Unit circle. how would you locate this question in the unit circle? What would you be looking at to answer it? 1/2 when, where would you see the 1/2 in your unit circle all like drawn out? Okay, go find the unit circle. Where is it? 4.1? Double check table of contents. I think it's 4.2? So do you guys have your patty paper close? Look at your unit circle. You can even look at 30 degrees because you know that's an answer. Where's the 1/2 showing up? Oh, maybe some of you guys didn't write it. Where's the 1/2 showing up at 30 degrees? Where is it? I see Ruth pointing to it. Where is it? It's in the order pair, right? What part of the order pair? The y value. Good. But my question to you was to find all the places where sine of x equals 1/2 in the unit circle. Is 30 degrees the only place where sine equals 1/2 in the unit circle? Where else does it equal 1/2? Oh, careful, not 60. That's where cosine equals 1/2. Where's the y? Pi over 5 pi over 6 or 150, right? I think I heard that from, good. So I have 30 and 150, I have pi over 6 and 5 pi over 6. So all of a sudden, even though 30 degrees was right, or pi over 6, two different ways of writing it, in a unit circle, 150 would have also been right, 5 pi over 6 would have also been right. So even though the calculator gave us 1, was the calculator wrong? No. We talked about before break how the calculator can only find us one answer. It can find us the principal answer, the restricted answer. There are only certain quadrants that inverse trig would give us answers from. So inverse sine only looks at first and fourth quadrants. It wouldn't even look over here. It's defined to ignore this side of the unit circle. So the calculator wasn't wrong, it just couldn't give us all the answers. So right now we have more answers. Right now we have 30 degrees or 150 in degrees. And then in radians we have pi over 6 and 5 pi over 6. And guys, this leads us to the notes. Directions are going to lead you as far as how many answers you should find. The directions are going to lead you to how many answers to find. Now, first of all, let me have you guys look back at the beginning of section 5.2 real quick. The very first page of 5.2. Go ahead and flip back. We talked about how there are two different types of equations with trigs. Two different types of equations with trig. Which type, okay, we talked about this equation before. Which type were we using t-proofs to show why it's always true? Identities. So what do you think we're going to be working with in section 5.3? Conditional. So we're not saying always true. What we're being given is something that's only sometimes true. We're going to need to find the sometimes, we're going to need to find the places where it's sometimes true. And the sad thing is there's infinitely many places. They're restricted only at certain locations, but we can represent them infinitely many ways since angles keep on growing and growing and growing every time you spin more and more revolutions or rotations. So, using what we've done right over here, in your notes, ready? If you were solving for all of these examples, or I should say for all of these directions, it's for the exact same problem. If you were given the directions, just solve with trig inverse, meaning, if you were given the directions, hey, just solve sine inverse of 1/2. If you were given the direction, solve x equals sine inverse of 1/2. You would have to answer like your calculator does, the one principal value. You would have to answer in the first quadrant. Just take 30 degrees or pi over 6. And that's it, you'd be done. One answer. Degrees, radians, means the same location. One place and you're done. And so remember, when your calculator, whenever you put in an inverse trig to your calculator, it's only showing you half the picture. It's only showing you half of one rotation. Now, what if they were to give you something like solve for all angles within negative 2 pi to 2 pi. They give an interval, negative 2 pi to 2 pi. First of all, they're telling you only do radians, because when they say negative 2 pi to 2 pi, that's going to be radian measures, not degrees. That means they don't just want the one answer the calculator will give you. So we could look over there and say, okay. In the unit circle, if I go 0 to 2 pi, if I look at one time around the unit circle, looking at all the angles through the first quadrant, second quadrant, third quadrant, fourth quadrant, there are 2 times, looked at our unit circle, there are 2 times sine's going to equal 1/2. So we could say sine's going to equal 1/2 at both, well, hold on, radians, pi over 6 and 5 pi over 6. But guys, what's the dilemma with that if I stopped there? Yeah, that was only going from 0, angle 0, to pi over 2 and pi and 3 pi over 2 and 2 pi. That's just going from 0 to 2 pi, but what did they say I was supposed to look at? Negative 2 pi to 2 pi. Well, how do I go negative at angles again? Rotate the other direction. So then I have to say, wait a minute, these are just the angles going to positive 2 pi. Are there any angles going the other direction? Well, then let's think going the other direction. Yeah? If I was to go this direction, are there any angles in the fourth quadrant? How about the third quadrant? How about the second quadrant? Yeah. Okay, well, what angle would that be if I went negative this many?
Negative 7 pi over 6.
Good. It is at 5 pi over 6 if I went the positive way. It's a little bit less than 1 calzone. But if I go the negative way, isn't that 1 whole calzone, 6 out of 6 and 1 more?
Yeah.
That's going to be negative 7 pi over 6. I have to go negative 1 whole half circle and a little bit more. So I have negative 7 pi over 6. And how do I get to, aren't I going to have to keep going?
Negative
11 pi.
Good. As I go 1 full rotation backwards to get the negative 2 pi, I have to go hit this one, negative 7 pi over 6, and this one, well, it's all 12 minus 1, so 11. Negative 11 pi over 6. So here's a trick for using these directions or being given these directions. When they tell you from one angle to another, usually I start at 0 in my head, because 0 is where we almost always start, right? Standard position, start here, and then we rotate up or down. So I say, okay, look at all the angles between 0 and 2 pi. That's usually the easiest one. That's the unit circle, 0 to 2 pi. But then you got to ask yourself, wait, do I have to go negative also? So go that direction. Guys, the calculator can't give you this. Well, it kind of can. You want to see how it kind of can? Calculator's open. I want you to graph sine of x as y1. Just plain old sine of x. Then I want you to graph 1/2 as y2 and make sure that you're in radian mode. The calculator can give this to you. It's not super pretty how it gives it to you, but it can. Let me go grab it. I'm going to go ahead and move it on this side of the screen. That obviously didn't quite work. Okay. So you're in radian mode. I'm checking mine. Oh, nope, that's not going to work. Radian mode. You're going to make sine of x equal to your y1. You're going to make 1/2 equal to your y2. You can do 1/2. You can do 0.5. I'm considering real quick my window. If I do like a zoom standard, 1/2's okay. It goes between negative 10 and 10. And I'm going to go ahead and graph it. Question. How can I tell on a graph when one function will equal the other? Intersections. And do I have a feature in my calculator to help me find intersections? Yes. Now pause. How many intersections do you see? I see 1, 2, 3, 4, 5, 6, maybe that one 7? Wait. We only found 4 answers. How can we tell our calculator exactly where to look? Couldn't you zoom in? Now, we can't pinch and zoom, but what can we do? How can we change our window? X is horizontal. X's have a range. What was the range or the interval for the X's? So tell the X-min to be like, hey, I only want you to look from negative 2 pi, if I can get it to do it, negative 2 pi to 2 pi, right? Now let's look at our graph. I I see 1, I see 2, I see 3, I see 4. I bet they're the same as those ones. Now what's gonna happen though, wait, how do we do intersections again? You guys remember, right? Second trace. Intersect, number 5. How do we answer these questions? Okay, I'm on the sinusoidally one, right? So I can say first curve, yeah, sure, the sinusoidally one. It jumps to the line now. Is that the second thing that I want? Yeah, I want both of those. Enter. Guess, what am I gonna do? Well, that's annoying, right? What's gonna happen if I just hit enter right now? You guys probably don't know. It's gonna find the closest one to wherever I am. I could go all the way over, Okay, guess-ish, go, enter. What's bad about this answer versus this answer? Yeah, it's a weird decimal. I mean, could we go back to the home screen and say negative 5.75? All right, let's try all the different pi over 6s, and maybe you would guess right away 11 pi over 6. Maybe you wouldn't guess that one right away. Oh, hey, it's the same thing. Sadly, calculator doesn't show you that though, right? So it's kind of annoying, but you could double check. What's something else you could do to visualize it a little bit easier and not have the weird 5.75 blah, blah, blah for 11 pi over 6? You could do second table. I think you'd still see decimals though. Like no matter how you did it, and you could start plugging in different values, like, hey, I'm gonna try all my unit circle values, like 0, and then let's try like pi over 6, and let's try like pi over, you're like, oh hey, pi over 6 ends up giving me 1/2, I think. Okay, yeah, that's the one that'll match, and you can keep on going. That would be kind of hard though. Can anybody think of anything else that would make it easier for us to visualize what these angles are? You could go degree mode. The only problem is if you go to degree mode, are you getting your final answers? No, but you are getting an idea. That would probably be a little easier. So you could go to, yeah, same two functions. Now I'm in degree mode. Why is this picture going to look so different though? What's negative 2 pi to 2 pi in degrees? Negative 6.28 degrees to 6.28 degrees? Does that help me at all? What range would I need for degrees if I was doing degree mode to be the same or equivalent to this? Yeah, I'd have to change my window to be negative 360 to 360. Do you guys remember a special zoom that might help us if we're in degree mode and it looks all funny? Zoom fit, maybe. I was thinking zoom. Yeah, if you look in your zoom menu, there's a zoom trig. It kind of like makes it appropriate to whatever mode you're in. That might help. But do you see how we have the exact same picture now that I did negative 360 to 360? And what would happen if I did second trace intersect? This time, would it give me a nasty decimal or a nice pretty angle? I have to do my first curve, second curve. It's not going to be able to give me 11 pi over 6, but it is going to give me negative 330, and I could then try to convert negative 330 degrees to radians, and then we'll get negative 11 pi over 6. So long story short, can your calculator help you find more than one angle? Yes. Using sine inverse? No. Using a sine curve and a value? Yes. But you have to be kind of creative and strategic about it? Definitely. Okay? Now, here's a dilemma though. What's going to happen on this window if I zoom out and go to like negative 720 to 720? How many more intersections, or just am I going to have more intersections on the sine curve? What do you guys think? Why does that make sense? If I keep on zooming out and zooming out and zooming out, I'm going to get more and more and more intersections. Why is that true?
More rotation.
Yeah, you're going to be including more rotations, and more rotations, you're going to have it crossing through the first and second quadrants again and hitting those locations. So here's the dilemma. Here's the last type of directions you might see when solving conditional equations. What if they say find everybody? Oh, dang. Why is that bad? There's infinitely many answers. Now pause. Even though there are infinitely many answers, how many locations are these answers occurring at? Careful. 2. only, remember, only the first and second quadrant. It only occurs here and here. Now, can you keep rotating forever? I mean, not practically, but mathematically, logically, yeah, you can keep rotating however long you want. So how do we use this idea of only having two locations, but then all of the infinite rotations? Do you guys remember something about coterminal angles and how to write them? Ooh, that was from a while ago. Coterminal angles. Here's what we can do. For all angles, like all angles, not limited by an inverse function that only allows one, not limited by an interval, but all, we would say, cool, take the first quadrant one, pi over 6, take the second quadrant one, and say, you know what, there's this cool notation representing coterminal angles that says, take this location and add however many 2 pi's you want. Subtract however many 2 pi's you want. Remember the notation there? Start here. How can I say add however many 2 pi's you want? You can add 1, you can add 2, you can add 3, you can add 4. There's a variable that we can put with the 2 pi. Anyone remember?
N?
Yeah. Thanks, Laney. N. Where n is an integer. You guys remember integers? Positive or negative counting numbers? So n could be positive 1, n could be positive 2, positive 3, positive 4. N could be negative 1, negative 2, negative 3, negative 4. This represents you're rotating once, rotating twice, rotating 3 times. What can I do to this guy? Same thing. And I just expressed the infinite in 2 little sentences. Now we've used n before, so I didn't really state him, but I could say that n represents all possible integers. And there is that snazzy notation for integers if you really want to use it with the z, but you could also just state all integers. Okay, what was all of this for? All of this was for getting you guys to be able to read the directions and know what kind of answers they're looking for. If they give you an inverse trig written out, you're only allowed to give one answer. And that was from the inverse trig section in chapter 4 that you can review. But if they start giving you intervals, they're looking for more, and you're going to have to use your unit circle knowledge and think about what angles are they talking about, what quadrants do they go through, and do they match any answers that the inverse would give you. And last but not least, if they want all, you have to think about what are the locations where it's going to happen, and then how do I add the coterminal angles. Okay? So for that, you guys have your directions of how to isolate, or how to solve, how to approach a conditional equation. Try to get the trig by itself. If you can't get the trig all by itself, aka if you can't get the x contained in one trig function all alone, then you're going to have to use some of the skills from 5152 to change it up. Like that equation that we looked at the beginning of class. So I'm going to go ahead and I'm going to move this slide out of the way so that we can still see the directions when we get to something like our first example. Well, let's move this guy out of the way too. This way, say you can look at the unit circle, or you can look at like what your graphing calculator would give, but we actually already demonstrated that, so let me move that out of the way as well. All right, here we go. First example. Solve the equation. Let me make this particular. Solve the equation for all angles. So, solve the equation for all angles. Question, what camp does that put it in? One answer? As ever many as work, or all? Yeah, all means all means all. So not all but limited, but all unlimited. Alright, kiddos. Solve the equation. It's not a T-proof. It doesn't say verify. It doesn't say prove. It just says solve, which means it's only sometimes true. We get to move stuff all over the place. We don't have to stick to one side. Yes. So what can you do? Add. Yeah, you guys like it? Don't do inverse yet. Gotta get the trig all contained, all on one side, x in one trig function. So, we're allowed to add. Cool beans. I heard add first, that's why I'm doing it. So what do I get?
2 cosine.
Yeah. 2 cosine x plus 1. A lot of you guys wanted to play with both sides of the equation during the T-proof stuff. What do I do now? Yeah. Subtract the 1 from both sides. And all of this is in hopes of isolating the trig function. Our last step would be divide by 2. So now I have that this beginning equation is only true when, remember sometimes true, only true when cosine of x equals -1/2. Because we had to subtract the 1 and divide by 2. Okay, ready? Pause in your groups. I want you to think about the directions, how the answers are supposed to look. And you can look back in your unit circle if it would help. Or you can go to your calculator. It might be kind of tricky though. I would suggest unit circle. Let's see if we can get some expressions for all the answers. Ready, set, go. This is very similar to this one, just now cosine of x equals -1/2. When does that happen? Where does that happen? And how can you write the answers? Let me go unit circle. Who has a unit circle?
Percentage y.
1, 2, 3,
Someone open up the unit circle. Is cosine x or is cosine y in that unit circle? Oh, wait. Yeah, cheater chart. Okay, just give you an idea.
I'm asking you.
Oh, wow. So then you have to think, also you must take calculus. 4 pi
4 pi over 3 is I'm telling you.
cosine is positive.
4 pi over 3.
So let's look at this little table of 50 years. Remember there are x's and y's, right? Adding cosines
This is 4 pi over 3.
So when is x
Pi over 3.
in equal to
You can
negative?
have more than one answer.
That makes sense. Or cheater chart.
4 pi over 3 pi
1,
over
2,
3.
3, 60 degrees. But I need -1/2. So what quadrant do we do this? Well, all angles, remember we just looked at one time around to find the locations, and then we added all. If they give us like a little bracket, then we have to be specific.
Yeah. Nobody's saying
I mean, you could write -2 pi n, because then a negative times a negative will be a positive, a negative times a positive, like it'll have the same answers. If you put minus or if you put plus, since n can be all those different numbers. But the nice thing is we just put plus. What do you do? By common notation. Do you guys figure out what quadrants cosine is negative?
Yeah.
Which ones? 2 and 3. Good. And then which reference angle? Was it a 30, a 45, or a 60?
30.
No. It was an over 3, which is a 60. Good. If you were looking in your unit circle, that's where the x would have been a -1/2. If you were looking in your unit circle, that's where the x would have been a -1/2. Cheater chart. 3, 2, 1, 60 degrees is where this is going to happen. You had to know the second and third quadrants. So then, what angles and radians would those be?
2 pi over 3 and 4 pi
and
over
4 pi over 3.
And why am I writing only these two? Because those are the only two locations. Spin however many times you want. You gotta land here or here for cosine to equal -1/2. So how do I show all the coterminals? Got it. Does that make sense how we follow the directions?
Yes, ma'am.
All angles, infinitely many, identify the locations, and then plus 2 pi n. Why didn't we just list whatever works? Because they didn't tell us a beginning end. All right, fine. So we just looked at 0 to 2 pi, looked at one unit circle rotation, and figured out our locations, and we were done as soon as we wrote our coterminal angles. Done. Okay. Thanks, everybody. How about, let me keep moving this real quick. Even though it's a little bit annoying, I apologize. Let's move this guy down. Alright, I'm going to change the directions on this one. For all angles within. Alright, this time I'm going to say within negative pi to pi. Alright, the directions have changed just a little bit. I decided to now go with solve for all the angles within negative pi to pi. I apologize, my little cursor's in the way. Negative pi to pi. Now, hold on. After you get the directions down, put it in a camp. Alright, so I'm looking for all the possible, I'm going to have to think about these angles. Guys, before we even approach the equation, let's think about those angles. Where am I looking in my unit circle? Or in what quadrants am I looking? Good, starting at 0 and going to pi, I'm going to be looking in quadrants 1 and 2. But then I have to stop there, right? Because I can't go past pi. But what else do I have to look at? I have to go to negative pi. So am I going to cover all 4 quadrants? Yeah. But I'm going to look between 0 and 180 and 0 and negative 180. Okay? Now pause. We don't even have a statement to think about yet. So let's go over to this equation and say, stink, I need to get the trig all contained in one place. Remember what we talked about? What are we going to do to try to start solving this? Okay, let's change sine squared. With Pythagorean, what did we say? Do you guys remember who the sine squared equal?
1 minus cosine squared.
1 minus cosine squared. Remember, the better you know your formulas, the faster this can go, yeah? Okay. This isn't a T-proof. It's not sticking to one side. So let's move stuff around. What are we going to do? There's some of you that see it. I know you see it. What can we do? We want to get everything together. Yeah, add. Good. Add the cosine squared. We're allowed to move things. We're solving an equation. We're not doing a T-proof. So let's add to the other side because they're like terms. And what do we get if we have 3 plus 1? 4. How do we get the cosine morlum? Divide by 4. But now stink. We're stuck with that nasty squared. Now what do we do? Square root. Yeah. Now careful. If I square root a squared, technically it's that nasty absolute value thing. I'm just showing you where the plus minus comes from. You guys got used to a plus minus, but maybe you didn't realize why. When you square root a squared, it's technically the absolute value of cosine. And do you remember from, well, hold on, do you know the square root of 1/4?
1/2.
1/2. Square root of 1 is 1, square root of 4 is 2, 1/2 times 1/2 is 1/4. The reason we do plus minus is because the square root of a squared is absolute value, and back from Algebra 1, we solve absolute value equations by setting the inside equal to the positive and to the negative. Or you could have thought plus minus square root both sides. It's technically a shortcut to the actual working through of why plus or minus. But all of that to say, didn't we just talk about when cosine was 1/2? 3, 2, 1. What angle was that? 60 degrees or pi over 3s. And all of a sudden, this whole plus minus thing says what quadrants are legal? All 4. They can be positive or negative, all 4 quadrants. So therefore, we're going to go ahead and say, hey, we need this 60 degree, we need that 60 degree, we need that 60 degree, we need that 60 degree. But how do we state them properly? Only the angles between negative pi and pi. We could do pi over 3. That's technically the third in this interval if you were going to go in a number line. Chris, you were saying negative 5 pi over 3?
No,
Careful, that's bigger than 1 pi, so it's too big.
Negative 2 pi over 3.
Ah, negative 2 pi over 3. Is that the first one under pi? Yeah. So think, negative 1 pi over 3, negative 2 pi over 3. And I can't go beyond because of this cutoff. Who else is negative? I have negative 1 pi over 3. So who am I missing? I have negative 2, I have negative 1, I have positive 1, and now I need
2 pi over 3.
no 2 pi n's because I'm only allowed to have the ones that fit. Does that make sense? Okay. So when you get to homework, you're going to have to think about what are my directions and fit it in a camp. Which set of directions, and that's what my answers need to look like. And the last one, it was all angles. My answers looked like this. They were a little different, but they looked like that. This one, where I said within, I'm only cutting off and looking at whatever works, so then it looks like that one, right? But we just have to use maybe some transforming to make it legal, and then some unit circle to attach what we need. Now, one more time, could you have graphed this is y1, this is y2 in degree mode, found all the degrees, and then transferred them? Transfer's not a good word. Converted them all to radians? Yeah, you could have. It would take a lot of time, though. But if you ever get stuck on a problem, that is one way to get to the end and then try to figure out and work backwards. Joel?
Stupid question, but like, why would you do all the work like under that equation if you just know like the points have to be between negative pi and pi? Like, can't you just kind of figure that out?
Well, the problem is, since you know the answers are going to be exact, maybe you could look at this and maybe you could actually go through and say, okay, I know sine sometimes is 1/2. So 1/2 squared is 1/4. And then cosine sometimes, well, when sine is 1/2, cosine is √3 over 2. You could technically go through each possible pairing in the unit circle and plug in. That could be like on a multiple choice question of a test if you're stuck. That's a way to check it, right? But some of these equations might get down to where it's not unit circle. Like let's say this was 1/3. All of a sudden, that just opened it up to every possible angle I'd have to use my calculator. And then if you did the other way, you're kind of screwed because then you just are testing the wrong things.
Gotcha.
Does that make sense?
Yeah, thank you.
Yeah, good question though. And it wasn't dumb. How about this one?
Yeah.
What if I was to say, let's have fun, 0 to 3 pi. We can look at that 0 to 3 pi and say, hey, what camp does it fit in? The top, the middle, or the bottom? Yeah, the middle one. So I have an interval. So it fits in the middle camp as far as what directions I'm following. All right, well, I mean, I guess I could look at my unit circle and I could think about where I'm looking. 0 to 3 pi. I'm looking first, second quadrant, third, fourth quadrant. Ooh, and I get to keep going? All right. That's 0 to 3 pi, right? 1 pi, 2 pi, 3 pi. But that's not going to help unless we have something to test. So what do I do? Distribute. We could try to distribute, which I think some of you guys are thinking when you said FOIL. But first of all, do these two match perfectly?
No.
Now, we haven't really talked about how there actually is a formula out there. We'll see it in section 5.4 that would let us do something and change this guy up. But for right now, you don't have to distribute. Question: how would you solve, don't write it down, something like this? How would you solve that? X plus 2 times x minus 3 equals 0. Oh, you wouldn't FOIL, would you?
No.
Negative 2 and 3. You would set each one equal to
0.
So what are we going to do
Set to
here?
0.
Set each one equal to 0. Now, if it wasn't all nice and factored, well, maybe we'd have to factor it and then set each one equal to 0. But since it is all nice and factored, well, let's just use it. There you have it, exactly how I want it. I want each one multiplied together so I can set equal to 0. You guys okay if I ... and say cosine of x equals negative 1/2?
Yes.
Subtract the 1, divide the 2. This one's the struggle, and I'm glad we're ending on this one today.
Yeah.
Because you're like, what? Here's what I want you to think of. I want you to think of cosine inverse. What if we were just to have like cosine of blah equals 0? When does cosine equal 0? ignore the 2x until we can figure out when cosine equals 0. So if you want, you can think of cosine inverse. That's kind of what we're doing to get rid of that cosine. Cosine is the x, right? When does x equal 0 in our unit circle?
Pi halves.
Yeah, pi over 2 right here. But actually, it could also equal it if we were, because we need to look for lots of angles. How about 3 pi over 2? How about 5 pi over 2? How about 7 pi over 2? Uh-oh, we're going to run out of room. Why am I writing so many answers, especially, well, 3 pi. Hold on, kiddos. 3 pi would be how many halves? No, not 3 halves. 3 wholes is how many halves? 6, good. Multiplied by 2 over 2. Multiplied by 2 over 2. So 3 pi is 6 pi over 2. Oh, that one doesn't matter. Well, hold on. If I plugged in pi over 2 to this, wouldn't that be, the 2's would cancel, wouldn't that be pi? Pause. If I plug pi over 2 into the x, wouldn't the 2's cancel and I'd have pi? That's not good. Here's why. I need 2x to equal this guy. So after I start getting all my answers, guess what I have to do to every single one? Now the nice thing is dividing by 2 is the same thing as multiplying by a half. So really I'm just saying, oh, you know what? Pi over 4 plugged in would get me pi over 2. 3 pi over 4 plugged in would get me, the 2's would reduce, 3 pi over 2. 5 pi over 4, now hold on. What would 3 pi in fourths give me? I have to go further than I thought I would. So I'd have to include more angles until I can cut it off. We already solved this one down here, guys. We put them all together, and those would be our answers. Did a great job. We started 5-3. Start homework this weekend. We'll finish 5-3 examples on Tuesday through Wednesday. Start little by little. Still in Chris, don't forget Tuesday after school. What? Bye, everybody. Happy Friday. Quiet people. Have a safe trip and a good time. Stay healthy.